Student, in this video I am going to talk about attribute selection with information gain. Generally, for a data set with large number of instances which are described by attributes, and there might be a target variable. Target variable means labels, or you can say class labels, or you can say class names. We can determine which attribute is the most informative. So using those class level and class names or target variable, we can determine which attribute is most productive or most informative with respect to estimating the target value. We will also, there is a way to rank. There is lots of different way to rank a set of attributes by their informativeness. Point is that if you have, suppose, 2000 attributes, suppose 1000 attributes, then among all of them there are some attributes which might not be useful enough to include in the classification process, to include in the learning process, to define or to find any solution of the problem, or to find a target value of the problem. But few attributes might be very informative. So we need to rank the attribute as per their informativeness, to in particularly by their information gain. Information gain means how much information we can get from that attribute, and how it will help us in finding the target variable. So that is what is very important thing before diving into learning process. It is very much important to know which attributes giving more information, which attribute not giving such information, or just it's giving redundant data. So to illustrate this information gain, we'll start with an example, simple but realistic dataset taken from machine learning datasets repository in University of California at Irvine. You can see this dataset. You can see it in this marking. It is a dataset describe edible and poisonous mushroom taken from the Audubon Society Field Guide to North American Mushrooms from description. So it describes the dataset here like this. This dataset includes description of hypothetical samples, okay, corresponding to 23 species of grilled mushroom, 23 species of grilled mushroom in Agaricus and Lepiota family. So these two different family, okay, from these two different family, they collected 23 species of mushroom, which is grilled mushroom, and each species is identified as definitely edible. So each species, these 23 species, are identified or labeled as definitely edible and definitely poisonous, or of unknown edibility or not recommended. Point is that every species is labeled with this information. This later class was combined with poisonous one. So here you can see the third one, third probability, that mushroom species might be or unknown edibility or not recommended for eating, is combined with the poisonous one. So the guide clearly states that there is no simple rule to determining the edibility of mushroom. No rule like leaflet tree or let it be for poisonous and oak EV. So there is no specific kind of rule to find out which mushroom will be edible or which mushroom will not be edible. So each data sample in one mushroom sample described in terms of its observed attributes, features. So for each data sample, instances is one mushroom sample. Suppose there is 23 mushroom samples, there will be suppose 23 instances, or might be for each mushroom species there will be lots of other instances also, and for every instances there might be lots of or several attributes. The 20 odd attributes and the values for each are listed in table 3.1. We'll see that, but see the description here first. 20 odd attributes are collected, or you can say 20 odd features are collected, and values for each one are listed in this table. For a given example, each attribute takes a single discrete value. Suppose gill color is black, means color of the gill of the mushroom is black. That type of feature is included. We use 5644 examples, or we can say 5644 samples from data set, comprising 2156 poisonous, 3488 edible. If we add them, 3488 plus 2156, that is equal to 5644 numbers of samples or examples. Okay, same name, or instances, same name, and having 20 attributes. So this is a classification problem, because we have target variable with and target variable is edible or not edible, or you can say opposite way, poisonous or not poisonous. But not poisonous might lead to another question, is that it might be not poisonous but not recommended also. That type of things also occur. So main question actually arise like that, whether the mushroom is edible or not. So with two values, yes or no. Yes would go edible, no for poisonous, specifying our two classes. Each of the rows in the training set has values for this target variable. We will use information gain. So here we will this term to answer the question, which single attribute is most useful for distinguishing edible mushroom from poisonous one. Means we will try to find out the attribute which is most useful for distinguishing these classes. Okay, so this is a basic attribute selection problem. So basically we are going into the attribute selection problem. Okay, we are going into the attribute selection problem. In much larger problems, we could imagine selecting base 10 or 50 attributes out of several hundred or thousand. And often you want to do this if you suspect that there are far too many attributes for your mining problem, or that may near not useful. Here for simplicity we will find a single base attribute instead of top 10. So here you can see that in this problem the discussing is that they are going to choose only one, but sometimes you can go for 10s or 20, a set of attributes, not all the attributes, because all the attributes might not work in your mining problem. So that is why this is a attribute selection problem. So table 3.1, as mentioned here, attribute names are like this, possible values are like this, like for cap shape is bell, canonical, convex, flat, knob, sunken. Possible values are these. For 20 different type of attributes, 20 different there are very numerous type of possible values are there. Okay, so in that way there is target variable yes or no. So that is the dataset description, or you can say this dataset description, for because these are the attribute and these are possible values. Okay, since we may measure information gain, this is straightforward. We are asking the single attribute that gives highest information gain. So our equation is what? Can you say that? 3.2. Our equation is 3.2. Now where the equation is 3.2. Here. So actually this information gain is calculated as like this. Suppose this is parent and children two variable, entropy of parent minus probability of C1 into multiply with entropy of C1 and probability of C2 into entropy of C2 plus like that. So information gain is calculated using this equation, but in this equation you can see the entropy also. Entropy is calculated using this, okay, P1 log P1. So entropy is actually is a measure of disorder that can be applied to a set such as one or individual segments. Consider that we have it's not like that, like the most common splitting criterion is called information gain, and is based on a PUD measure called entropy. Both concepts are invented by one of the pioneers of information theory, Shannon entropy. That is why, and entropy is measure of disorderness, or we can say here actually P1 P2 these are the information. Okay, here on example you can see, as a concrete example, consider a set of S of 10 people with 7 of them non-right of class and 3 of them right of class. So what is the entropy of non-right of and what is the entropy of right of? So here you can see entropy of S. So the entropy of S means that set S of 10 people, 0.7 into log 2 7 plus 0.3 into log 2 log 2 0.3, and that is minus, entropy is in negative. So that is value is 0.88. So that is the entropy of this entropy value. Highest entropy of this situation is 0.88. okay, so in that way we can see in the information gain also, suppose parent and children. So we will try to find the entropy of parent first, then minus the entropy of the children, and there might be lots of other children also. So if there is contain only one children, then entropy of these children. So in that way we will try to find out the information gain. But here in this equation you can see that it is, you are seeing that it is trying to find the entropy of children also in this equation. So this is the equation to find the information gain. So using the calculation of information gain achieved by splitting one each attribute, information gain from equation 3.2 is defined on a parent and a set of children. So as we discussed, this, we can apply that in the parent and children example previously. You can see in the book also. The parent in its case is whole data set. First we need to find the entropy of parent and entropy of the whole data set. If two classes are perfectly balanced in the data set, it would have entropy of 1. Mean perfectly balanced mean probability of finding that parent or children will be almost equal. The data set is slightly unbalanced. Here in this case of edibility question, the data set is slightly unbalanced and more edible than poisonous mushrooms are presented. So, and its entropy is 0.96. So it says that in this data set, data set about edibility of mushroom or edibility of mushroom or not. In that case, the entropy is 0.96. It means that slightly unbalanced. If it is 1, then you can say that it is balanced. To illustrate entropy reduction graphically, we will show a number of entropy graphs from the mushroom. Figure 3.6 and figure 3.8. Each graph is a two-dimensional description of the entire dataset entropy, as it is divided in various ways by different attributes. On the x-axis is the proportion of the dataset 0 to 1. On the y-axis the entropy also 0 to 1 of a given piece of data. The amount of shaded area is in its graph represent a amount of entropy in dataset when it divided by some chosen entropy. Here you can see default entropy for mushroom. So that is 0.96 in the data set. That is why this is not 1. Okay, proportion that is set as 1. Okay. Entropy sort of the entire mushroom, the entropy of the entire data is 0.96 of the area is shaded. Okay. And then you can see here entropy and prevalence of values of gill color. Suppose we are taking the gill color here, first attribute. Entropy sort of mushroom sort is like this. Does amount of shading correspond to total entropy weighted sum with each bar corresponding to the entropy of one attribute value. Suppose U is for one attribute, one value of the attribute, N is for one value of the attribute. Okay, in that way we can say proportion of the data, in that way we can say entropy of the data. So here you can see gill color. Gill color is this. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 attributes are possible values are there. But here you can see there is only like 1, 2, 3, 4, 5, 6, 7 attributes are here, which comprise the whole proportion of the data set. Okay, and some of them is lower in entropy, some of the higher entropy information is higher. So we can say is that here entropy of this one, of this P is higher. Okay, for entire data set the global entropy is 0.96, so the large shaded area below the line y96 we can take the this is 3.7 shows the data split apart by attribute gill color whose values are coded as yellow, Y yellow, U purple and brown and so on. The width of each attribute represents a proportion of data set that had value. Suppose here you can see this and N, P and N highest proportion you can see, and also W, but like K and U and Z are having less proportion on the data sets, but entropy is different. That it is saying the width of each attribute represents the proportion of the data set has that value, and height is its entropy. We can see that gill color reduces the entropy somewhat. The shaded area in 3.37 is considered is less than the area of 3.36. So here you can see this attribute, this whole shaded area, this area is less than this one. Okay, less than this one. So there is a difference between 3.5, 3.6 and 3.7. Now this is again entropy chart for mushroom data set split by spore print color. So there is another attribute. So we can see this attribute, this is the part. So in that attribute there are different type of values also, and different entropies for different type of values that is showing, and proportion also for different attribute, but this has also not 0.96 or entirely filled with the main attribute, main data set, that is this one 0.96. this is also not filled up. So figure 3.8 shows how spore print color decreases uncertainty and entropy. A few of values such as age, chocolate specify the target value perfectly and thus produces zero entropy bars, but notice that they did not account for very much of the population, only 30%. So here you can see that H is comprises only 30%, but but specify the target value perfectly thus produce zero entropy. If it is zero, it means that it produces the target very perfectly if it is zero. So you can see using this entropy and information gain, we can see how this showing us the value. And now figure 3.9 you can see, we'll see here. Okay, here shows the graph produced by order. So this is for order. Many of the values such as almond, creosote, musty produce zero entropy partitions. Only N, no order has a constant entropy 20. In fact, order has highest information gain of any attribute in mushroom dataset. So you can see this has highest information gain in entire dataset, because you can see that 0 is higher in this case. All these attributes showing 0 almost means they are perfectly targeting the target value, but not this one. There are some values which are not showing that thing, not at least in this case. So you can see that order case is showing that this is this targets the targeting value or target class, whether the mushroom is edible or not perfectly. So here you can see order has the highest information gain of any attribute in the mushroom dataset. It can reduce the dataset total entropy by 0.1, which gives it an information gain 0.86. What is this saying? Many orders are completely characteristics of poisonous or edible mushroom. So order is very informative attribute to check when considering mushroom's edibility. So that is the deduction we get from this example, that if we choose order because it is giving us highest entropy and highest information gain, but we are losing the information gain also, sorry, we are losing the entropy also by 0.1, which gives an information gain about 0.86. What this saying is that order is very informative attribute to check when considering mushroom edibility. So that is the thing we are getting from this one. So this is all about information gain and how we can find the information gain and how it is related with the main entropy. And because the equation is actually this one, this is the main parent entropy. Information gain is actually main parent entropy and the child variables. So in these cases, the child values are these are, but parent is this one. So to find out information gain, we need to find out by multiplying all these and subtract from main 96. So in this way we can find out an information gain. Okay. So and it gives us very good insight to find out which feature is very informative while considering while learning the dataset to find out which attributes gives more correct and perfect target. Okay, that's it all about information gain and attribute selection problem. And it is very important in case of large number of datasets having large number of attributes, thousands of hundreds of attributes. So please go through it again in this book. This is textbook 2. Okay, I have shared it with you in the Google Classroom. If you have any doubt also, please let me know.